So we have 22 degrees C at 19% relative humidity. Comes across at about 3 grams of moisture. It's about 30 kilojoules per kilogram. It's about right on 0.84. The specific volume, the density. Got a problem here. If I drive this all the way over here and try and find my temperature, it's off our scale. This is going to keep coming down, and it's basically, it says the air that's in here, if it was 20 degrees, has it been 20 degrees out for Fahrenheit recently? Minus 5 degrees C. That's sort of what the air in here is like. We haven't had a lot of air exchange since it warmed up to a whopping 1 degree C. So the air still hasn't totally changed out. It's still like what it was when it was 20 degrees out. If they had taken the air, if all the outside air came in here and they just heated it up right now, it would have this same amount of moisture in it. Now right now it's 95% relative humidity outside, which says it's the vapor pressure of the actual number of water molecules. Partial pressure of it is 95% of the saturation pressure at 1 degree C, which is cold. It's going to be really low vapor, like saturation pressure. When you heat it up, the saturation pressure at 22 degrees C is a lot higher because it's a hotter temperature. If it got all the way up to 100 degrees C, then the vapor pressure would be 1 atmosphere, 101 kilopascal. But the pressure didn't change, same number of molecules. If they just took that outside air and brought it in, we would have a whopping like 24% relative humidity. And what this tells me is we didn't, this air was from heated up when it was really cold outside, so they're not spending a lot of energy exchanging all the warm air for cold air just for the hell of it. So we're still dealing with the moisture in the air like it was when it was 20 degrees outside. Jason?
So our wet bulb dew point, you just go up and point straight left.
Dew point, yeah, dew point, you're taking the amount of moisture in the air and driving it to a temperature at which that pressure is its saturation.
So wherever it meets the saturation curve is your dew point?
Yes.
And then your wet bulb is the horizontal lines?
Wet bulbs takes the same amount of enthalpy and evaporates water, and when it evaporates, it drives the temperature down along, basically along that diagonal. So wet bulb follows the diagonal. Dew point follows the horizontal. Yeah, so one more time. The dew point is when you actually condense, so you're taking that partial pressure and driving the temperature down until it becomes a saturation pressure. So the moisture content doesn't change. You're cooling it, so you go horizontal until you hit the saturation curve to find the dew point temperature. Wet bulb would be if you had wrapped it in or if you have a washcloth and you swing it around and it's forcing the air around it to be saturated, but it's using the energy in the air, so it's the same enthalpy value being forced to saturation, and that's taking this enthalpy. So these are the lines for the amount of energy in the air. So the wet point's going to follow up essentially parallel to the enthalpy lines, which are those slanty ones. So part of the problem is what is this wet bulb thing? The reason the wet bulb's handy is because it's really easy to measure. It's really easy to measure plain old temperature, dry bulb, that's this scale, and it's easy to measure wet bulb because you just take a plain old thermometer, thermocouple. You could put a wet shoelace around a thermocouple and wave it in the air a bit. They actually have something called the Sling Psychrometer, which is a thermometer and then a thermometer with a wet sock on it, and you go like this and swing it in the air, and it forces the evaporation and it drives down the temperature of the wet thermometer. And then you take those two temperatures and you look them up here, and you can come into your state really easy. So the reason the wet bulb is handy is it's easy to measure. Yeah?
What does this do for the dry when the humidity is super high? Like today, like
It's not high.
dry?
Oh, you mean outside?
Yeah, like you know, walk out, your skin is super dry, lives, all that, even though
It's 100% relative humidity, but it's still really low moisture content. It's relative humidity. It's about the saturation. But this is the real number. This is how much moisture is actually in the air. So, you know, there's as much. It is dry.
Right.
You're dry out more when you're skiing than you are when you're
Right.
riding your bicycle or something in summer. Because every time you breathe in, you're breathing in dry air, and then you're breathing out moist air because your lungs have moisture in them. You'll lose half a pound or more. You lose more overnight in the winter just from breathing when you're sleeping than you would in the summer because you're more moisture, less moisture coming in, so there's bigger difference in moisture with each breath. I mean, you can see the moisture in your breath. You know, you can see it come out as fog, right? You have moisture like that. Okay. Now let's use it for something. I mean, great, we found all this stuff, big freaking deal, right? It's almost the case that you could take, what this shows me, there's more moisture outside now than there is, and, you know, things are melting and it's coming up. But this tells me that because the moisture's lower in here, they're not dehumidifying. It just tells me we're not exchanging a bunch of air, we're saving energy, we're not exchanging as much as we could have. So this is yesterday's air from when it was 20 degrees in here. So let's look at a problem. What kind of problem? Again, we are engineers. We don't cause problems, we solve problems. What if we have air coming in from outside and we got figured out we need to mix it with this much air and we want to see how much is going to actually come into the room. This is summertime, 32 degrees C, nice and warm, 60% relative humidity at that temperature. So I want to find the outlet state. And there's two things. I can find H value for this and a mass flow rate, and an H value for this and a mass flow rate of the air. And then solve the mass flow rate at 0.3 is going to be, I mean, well, let's look at, if you have mass flow rate going in here and a mass flow rate going in there, how much mass is going to come out here? It's the same. If I take the enthalpy times the mass flow rate here, that's going to be an energy coming in. If I take the enthalpy of that one times the mass flow rate, that's a total coming in, and I get a total going out. If I know the mass flow rate here, I can divide the total energy by the mass flow rate to come up with kilojoules per kilogram there. That's one of my data points. I can then find that's, you know, if this is the H on this one and this is the H on that one, I can figure out on this zone. The other thing we can do is the actual water content. So we do a conservation of energy on one case, enthalpy number, and conservation of mass on the water content. And with those two, I can find out what the enthalpy is here, find out what the mass flow rate of water, conserved mass of the water vapor, and triangulate to find that point. And there's a neat little trick we'll talk about too. Whoa. So, do the same thing on this one. Take a look and see what you see. I'm going to fill some of these in with the ones I saw, and we'll do some calculations, but see if you can make sense out of it. Dry bulbs. I don't really care about all the wet bulb temperatures and all that stuff. Looks like the first point's about 14 degrees at 100% relative humidity. Should get about 10 grams. For this one I get about 18 grams per kilogram of air. That's the water moisture. And I got first question is, what's the mass flow rate? So in point 1, if I have this volume flow rate, and this is cubic meters per kilogram, I can find my mass flow rate at point 1. So 50 meters cubed per minute divided by 0.828 meters cubed per kilogram should give me units of kilograms per minute. So 50 divided by 0.828. And for the other one, 20 meter cubed per minute divided by 0.890. What do we get? Number 828. Which one? 60.4. Another one, something like 22 and a half.
Yeah, 22.5.
22 point. I heard a 4 and a 5.
22.47.
Yeah.
5.
So, for our next trick, do the conservation of energy. What is the enthalpy at point 3? And by the way, mass flow rate, do you think we can figure out the mass flow rate at point 3 now? Maybe it's 60.4 plus 22.5, conservation of mass. So 82.9 kilograms per minute. That doesn't mean that it's 70 cubic meters per minute. It's going to be in that ballpark, but now we got like a different temperature. It's somewhere, you know, you notice there's differences in density because of the temperature. So we have to do it in terms of mass, not in terms of volume, because the temperature's jacking that all around. So that's this term, M1 times H1 plus M2 times H2 divided by 82.9. I didn't really have time to write it out, or room to write it out. But we can write the result. 15.3? 50? Yeah. Okay. Do we have concurrence on that? I seriously forgot my calculator. Again? 50.31. That's it. All right. For our next trick, we're going to do the same thing with the water vapor. Because how do we do that? The mass of water is the mass flow rate of air times the mass of air per, this is kilograms of air times grams of water per kilograms of air. This is the mass of water vapor passing through. Mass of water vapor coming in here plus the mass of water vapor there. Same process. You can find out what that value is. Multiplying these like that. Well, 12.17.
And that's the grains of water, right?
This one isn't grains. This is metric, and it's grams of moisture per kilogram of air, of dry air, meaning air without moisture in it.
Grams per kilogram.
Per kilogram. There are some of those scales are in grains. Some of them are in kilograms per kilogram. Some are in pounds per pound. So now, based on that, let's see. Look up, and what do we know? We don't know the temperature, but we know we got 50.3, so somewhere in here. We've got 12.2. I need a straight edge. Should be right about there. And the pencil's being recalcitrant. Oh well, it's being really drawn. There we go. So I'm going halfway between two marks there. Calling it 12.2 and 50.3. So the 50.3 line's going this way. 12.2 line somewhere in there, and they intersect right about there. And now I know I can fill in the rest of my state. Tells me the outlet's going to be at about 19.5 perhaps. Come down here, it's less than 20. 19.4 based on where I drew it. And we could find the density thing there, but the main thing is, we've located the point, now we know everything, and we did it. Conservation of energy on the enthalpy side, conservation of water mass on the vertical scale, and then we triangulated onto that point. And now we know this is the temperature at which the air is coming out of the mixture of the two. And we also know it's probably like 87% relative humidity, less than 90. And we got dew points and wet bulbs and all that to go with it. And here's the thing about it. We didn't actually have to do the two calculations. If you have two states that you're mixing, you can draw a line between them. It's going to fall on that line. And where on that line depends on the relative mass flow rates of the two components. So it's right on that line. All we had to do was either find the enthalpy or find this and where it intersects with the line between the two states. That's one of the magics of this graph. It just so happens that it works that way. But really, it's about the triangulation thing. But that's like gives you one less step. If you use the chart, I mean, you can find the information without the chart by doing what we did. But with the chart, draw a line, locate the 2 points, draw a line between them, find one or the other of those conservation of mass or conservation of energy, and where it intersects the line, that'll tell you the output state. And now we know the mass that's coming out. If we have this volume, now we know the volume's probably 0.84. It's more than halfway, call it 0.846. Now the volume flow rate coming out, we can figure out. It's not going to be exactly the volume flow rate of the two things coming in, because one was cold and one was hot. Now we're in between. It's going to be a little bit different than just adding those together, but the mass flow rate matters, not the volume. The volume changes with density. Density changes with temperature. So, questions about that? Making sense? That's how we do the airstream blending thing. You can get a lot more complicated than this. This is a known. What if you had a flow rate coming in and you knew what you wanted your output to be, and now you want to know what the mass flow rate should be of something coming in? What is the conditioned air supposed to be? That's where this stuff, we had two knowns, we're just adding them together. Now you got like multiple unknowns, simultaneous equation kind of solving thing. What if you had three? So in actual HVAC, you have to bring in outside air. You can recirculate some air. You need to condition the air. You can have conditioned air. You can take some cold air, mix it with the room temperature air, but you also have outside air. You got these three streams, and how do you adjust them? How do you design something that'll have a capacity for range of conditions? That's where it can start, and it's all about this kind of stuff. The basics aren't harder than this, but application of it, you can make it more confusing. So that's what that's about. So the quiz, or I'll talk it in lab today. There's two things going on. First, there's a FE 10-question multiple choice kind of a quiz that's sort of an assessment thing for me, but it's also for you guys, sort of getting a sense of sort of how they ask questions on the FE, that they aren't necessarily, well, when we go over the answers, I'll be really surprised if, and this is extra credit points that goes onto your test score. The average is usually about 30%, 40%, or something like that. So don't feel bad if, you know, I mean, give it your best try. But there's, that's why we do it, is to get you acclimated to that kind of failing. Yeah. There are questions on there that it helps to have your book. There will be some questions that need some data. There are some that look like they need data, and it's really just a conceptual question. So think first, step back from it. Do I just need to, think about it a little bit first? But I know that you're always under stress when you're being tested. But anyway, that'll be like a half hour's worth, and then we'll review it immediately, and so you see how you did. And then I use that data to see year to year if things are improving or getting worse, or what's better or worse. So that's what goes on in lab today. There were some questions about, yeah.
So you mentioned there would be two things. So that's one thing. What's the second thing?
What's on the finals? Anyone want to know?
I think we can think now.
Yeah, that'll be after we do the FE. We talk about the FE, then it'll be what's on the final. And this is part of it. 2 points. What are all the things? Yeah.
So is the final a separate perceptual grade, or is it just a regular test?
It's just another test. But, and so is it going to be cumulative? How can it not be cumulative at this point? I mean, it's just, we've been basically building all the course before now was building up to basically chapter 9 and chapter 24 a little bit, but it was that chapter 9 was really, interpolating, finding things on tables, all that. That's chapter 9 was just enabling us to do chapter 9, and that's what the test was about. So, is it cumulative? Yeah, but it's really just about chapter 9 and chapter 24. There would be one problem like this. By the way, humidity ratio here, if I took some air with this much moisture in it, and if I took that air that was at 32 and chilled it down to 14 degrees, what would my path look like? Yeah, because it's going to go, nothing's going to change on the horizontal scale. The moisture still stays the same until I hit saturation, and then it comes down. If I have a volume flow rate for the inlet, the 32 degrees C thing, I can come up with like a mass flow rate maybe of the air. We just kind of, we did that. Mass flow rate and a change in moisture, this would drop 8 grams per kilogram of air. If I know how many kilograms of air coming through, could I figure out how much moisture is dropping out of it? 8 grams per kilogram times however many kilograms are passing through the inlet. That's essentially what one of your, I'm giving it away. That's what your, this chart will be on the test. That's why we're doing it now. And then a couple points, and then how much moisture would be collecting per kilogram of air per whatever. That's part of it. Jason?
You were saying something about humidity ratio. So if you go all the way over, then you get the saturation curve. What were you talking about? You can go over that quickly. So I understand. So you said you give us a humidity ratio of 20 or whatever, and then you give us another humidity ratio. So those are our 2 points.
Well, there's relative humidity. That's more likely what you get.
Okay.
And how do they find the relative humidity? They find it from dry bulb and wet bulb temperatures. That's literally how, that's how you get those two temperatures, and then that's really how they measure it. And then they'll say it's a relative humidity. Usually what they'll give, like in the back of the room, it doesn't say here's the wet bulb and the dry bulb. It says here's the dry bulb and here's relative humidity. They didn't actually measure the humidity, I don't think. Probably. Well, maybe they did because there's no water in that thing. But when you find that point, then you find the humidity ratio is about, basically this is about water mass. It's a mass ratio. This is a pressure ratio. This is the partial pressure of the water ratio to the saturation pressure at that temperature. At that temperature, you know, what would be the boiling pressure, essentially, if you had it in vacuum. So this is a pressure ratio, this is a mass ratio. They're both ratios. But this is grams of water for kilogram, each kilogram of air. This is the partial pressure of the water vapor relative to the saturation pressure for water vapor at that temperature. That would be on your steam table, same number. Just the steam tables are kind of crude when you're only talking one degree at a time. Yep. Any other questions about that? I had a couple of questions about the lab, especially about the big water tank. And with a minute here, how much energy is in the tank? If I charge this entire tank, and if it's at this temperature, there's so many, like, we got a number, pounds per gallon. It's going to be around 8, but it's not exactly 8. You should have either density or specific volume, pounds per gallon. It's 1 million gallons, so you're going to have something on the order of 8 million pounds. How much heat can we store? How do we store heat? Is more mass give us more heat? If the mass is our thermal thing, more heat, mass related. If we have a bigger temperature difference, does that give us more heat? 20 degrees versus 1 degree for that same amount of mass? Yeah. And then there's a material property. And 1 BTU is defined as 1 pound mass degree Fahrenheit for water. That's how they defined a BTU. So you could say C sub P equals, for water, 1 BTU per pound mass degree Fahrenheit. And then one of the questions was, well, if I just charge it in 8 hours, you know, what's that equivalent to in cooling? 1 ton is 12,000 BTUs per hour. And now you could compare it to, so total amount of heat it's storing is its mass, C sub P, times 10 degrees, because it goes in, it discharges 55 to 45, or charges 45 to 55. And the rate at which you could discharge if you did it over the course of an 8-hour day. You charge it up at night, and that's one of the things. We have these coolers that have 4,000 volt motors, 3-phase 4,000 volt motors that are turning a turbine at multiple tens of thousands of RPM, and there's energy that it takes to do that, pumping the refrigerant, compressing it. If you charge it, you can charge this tank at night just by running through the cooler that's not part of the refrigerant thing. And basically charge this up for free without the electricity of the compressor. And then discharge it over, get this much heat. What's that equivalent to if those things are rated in tons? How many tons of cooling is that equivalent to? So, hopefully that's helpful. Oh, and pass in the aisle.
Professor, have notes and stuff in mind. Because everyone they do that. Yeah, and we'll just let it play on like this learning. Yeah. Unfortunately, yeah, I need that. And then just like oh, yeah. Yeah, that was the only thing I could remember was talking about.
Yeah. I came a little bit late because I was doing finish right now. I'm a little bit late. Is there any way I can get that table quiz that you just did?
Let's see, I printed up some extra ones. Where did they go?
Yeah.
Yeah.
Yeah, there you go. Got the thing on the top of it.
Yes, can I ask like the first entropy, this one? I just don't know like why it's like minus 10.8 of them.
Oh,
Is
it's not a minus. It's, you're talking about that? Oh wait, no, that's the wrong one. Where did it go?
this one is not an answer. Yes.
Oh, it's not a minus. It was like 10 and a half. It might be 10. That's a wavy gravy kind of a.
Yeah. So how can I check like I know like 30, but I don't know how can I.
Okay, so that was at 1 degree C. And 20, 18, 16, 14, 12. 10 is this line right here. It's a little bit above that. I don't have, my pencil was I couldn't get a sharp point on it, kept spinning on me, so I got to slow. But it was basically, it's more than 10.
Oh,
less than halfway, so it's less than 11.
oh, yeah, that's what I'm saying.
10 and a half-ish.
Alright, thank you, Professor.
Are you in machine design class like everyone else is?
No.
Ah, I bet you they're having a test.
Oh.
'Cause no one else showed up yet. You did okay with your presentation in English and whatnot.
Yeah.
But was it extra nervous to be doing that? That's one reason that's actually one of the requirements for accreditation is that there's presentation experience.
Yeah. It's good to do a lot of times. Better.
Yeah. So Hazel, was there a test?
Yeah, I was one of the first ones done, so I think I was going to do
Yeah. Test on the last day.
Yeah,
No final?
oh, we have a final too.
Yeah.
I think it was mean.
Yes, quite.